So now just a little bit continuing the historical context before we get into analytic combinatorics. So we started thinking about, Philippe and I met and wondered about how we're going to approach this problem of teaching algorithms in the early 80s or just before. I spent a year sabbatical in Paris. So as I mentioned, was certainly one part of the story was that there was a lot of opportunity and optimism to be successful in all sorts of venues with computation. Everybody knew that we were going to be completely transforming the world with our understanding of how to use computation effectively. And we had a basis, Knuth's volumes 1 to 3, were each 1,000 pages, just completely filled with wonderful information about both efficient and effective algorithms and methods for studying and understanding them. And we were looking for, of course, general themes and theorems that could be somehow explain the fact that we came up with the same formula. And at the same time, I realized that there were lots and lots of easy to learn, effective algorithms that many people needed to know. And I started my series of books on algorithms that many of which were not yet in Knuth's volumes, but still people needed to know and understand. So we had a big laboratory of possible things to study, and we're working for a living doing teaching and research, and we needed to educate our students. So that's where we kind of embarked on the project or the idea of that eventually led to analytic combinatorics. We didn't know that it would take 30 years. As I said, around 1980, we decided we should write a book. Well, by the way, everyone in computer science was deciding to write a book because there were no books. It's not like teaching math or economics or physics where there's plenty of books and you choose one. Computer science, there were no books. So everybody in their area that I knew had to write a book, and we were no different. And around 1986, I came to Princeton in '85, and the year after, Philippe came, and we taught a course on analysis of algorithms, and we had done some preliminary work on what we wanted to have in the book. But that's where, at least in Philippe's mind, for sure, it really crystallized that there was going to be something worth doing here. And we worked for quite a while. We had both of us had many other endeavors that we were involved in. And around 1992, it became clear that we had so much stuff that we were really going to have to do two books. One of them was going to have to cover the basics of analysis of algorithms, like deriving the Catalan numbers that I just explained. But the other one was going to involve doing some math. That is, there was a lot of research needed to really back up what was at the time some folk theorems or loose understanding of what goes on, but to actually prove facts was going to require some serious research in mathematics. And Philippe wrote a series of tech reports over the next 15, 20 years that really embodied a lot of that math, not to mention hundreds of research papers. And it wasn't until 2009 that the second book, Analytic Combinatorics, was finally published. So around 1995, the first book came out. That's an Introduction to Analysis of Algorithms book. In it was a fine coverage of many of the things that we felt were important for people working in the analysis of algorithms. Covering the basics for the kind of derivation that I just gave as an example, and preparing people, say, to really get the most out of Knuth's books and other research papers. So it covers recurrences and generating functions and asymptotics, and it talks about basic combinatorial structures like trees and permutations and tries, words and mappings, and all the basic things that you need for algorithms for sorting and searching, but other things like factoring and various string processing algorithms. So a fine way we felt to teach the mathematics needed to really do good scientific studies of the performance of computer programs. And so the question is, okay, that's a book. That's what we set out to do in 1980. Are we done? But of course, as I just alluded, what Philippe was seeing, particularly Philippe, in the 1980s, that we can get really, although the classical methods can give us everything that we need in principle, in practice, we can even do better because there are general laws, and it's actually possible to, in many cases, really skip the details. And in fact, the feeling was so strong that it really seemed like we should work towards the goal of automatically analyzing algorithms, thinking about some kind of black box that you just put in your algorithm and your input model, and you get out an estimate of the running time and have the rest of it done automatically. Of course, that's unattainable because of the halting problem, but it's amazing how close Philippe came to this goal in his research. So just a little bit more detail on what Knuth was saying about the analysis of algorithms. In his books in the 60s. So what he said was that you should have a good implementation that you understand, and you should have a realistic input model so that you can run experiments. Then you can go ahead and figure out the cost and execution frequency of each operation in the program. And then you can calculate the total running time by multiplying the frequency and the costs. Now, these things might involve some work, and they definitely would, but certainly in principle, you can go ahead and do that. And then you can run experiments to validate that your mathematical model of the input and the frequencies are valid, and that your analysis works. And believe me, we did this in many, many situations. For both Philippe and I consulted for companies and government, and our jobs were to go ahead and figure out how long a certain computation would take on a massive supercomputer, say like a Cray 1 or various other computers at the time that I could name. And we could do it. It was very exciting. It was very surprising that we could do it. We could say, if you're going to do that, it's going to take this amount of time, and then they would do it, and that's how much time it would take. We could be very, very accurate about it. Really, this is nothing more than the scientific method applied to the study of computer programs. And as I said, it's got the great benefit that it gives a scientific foundation for analysis of algorithms. And that we can go ahead and predict performance and compare algorithms and decide which ones to use and what kind of resources they're going to consume. And we have many, many documented success stories along these lines. But there's drawbacks too. First drawback is that getting a realistic input model is often, very often, the hard part. And the other one is that there's really a lot of detail in these kinds of analyses. So you did need experience and skill to get through these detailed analyses with generating functions and with asymptotics. And so, but the world is moving on. There's all kinds of innovation possible. So people were looking at other approaches. And one that has been extremely successful is what I refer to as the theory of algorithms. It was started out by Aho, Hopcroft, and Ullman in the 70s, and is widely followed textbook by Corman, Leishman, Rivest, and Stein today. That address the drawbacks in Knuth's approach in two ways. First thing was analyze the worst case cost of the algorithm. So provide guarantees on the running time no matter what the input is. That has the big benefit of taking the model out of the picture. If you can guarantee that the running time is low, you're in good shape. And the other thing they do is just do approximate analyses and really just use O notation and get an upper bound on the running time. That still provides a guarantee, and if that guarantee is low, you're in good shape. And it has the big benefit of taking a lot of the detail out of the analysis. And then go ahead and classify algorithms by these costs, the guaranteed worst case running time. And that was very successful. It enabled what one blogger called a new age of algorithm design. And there's literally hundreds, thousands, a huge fraction of our computational infrastructure started with studies like this. But there is a big drawback. And the drawback is that this analysis is usually, or often at least, not suitable for scientific studies. You can't really predict performance or compare algorithms if all you have is an upper bound on the worst case cost. It might be much too high, it might be a worst case that's not realized in practical situations, and many other problems. It's not what Euler or Poincaré or Stirling were trying to do, come up with precise predictions. So that's the context for really thinking about analytic combinatorics. Knuth was very successful, but kind of stuck with the model, and there's detail, excessive detail in the analysis. In Ahu and CLRS, they're working on worst case that might not be relevant, and the big O bounds, worst case upper bounds, are too loose to be useful in lots of situations. But what analytic combinatorics can provide is really a basis for scientific studies. It does it in two ways. Provides a calculus for developing models or input models that is very broad and extensible. That's number one. And number two, a lot of the detail can be encompassed in universal laws that are proven mathematical facts, but really take care of all the detail in the analysis. So that's the context where we're going to start talking about really what analytic combinatorics is.